Brunton from the University of Washington, one of the co-authors on robust flow reconstruction from limited measurements via sparse representation. His co-authors are Jared Callahan and Kazuki Maeda.
This is a little bit of a roundabout motivation for this paper, but it's really rooted in the idea that even very complicated fluids have low dimensional patterns, and those low dimensional patterns are identifiable from relatively few sensors. So instead of having to measure your entire fluid flow field, you can put a few choice sensors in key locations and get most of the information you would want to use for an engineering objective. And this is really kind of deep down motivated by insect flight. So flying animals, flying insects have sensors on their wings and on their bodies. They're not densely measuring the entire flow field. Insects especially have very sparse targeted sensors on their wings. And it's observed that this is enough information for them to infer relevant flow patterns so that they can control their body motion in that fluid. And so this paper, although not, targeted towards insect flight or sparse sensor placement optimization, we're taking a step back and trying to really understand what are just the principles of sensing partial information in a fluid and then reconstructing, relevant flow features in that fluid. And so we use singular value decomposition, proper orthogonal decomposition modes as the pattern basis, and then look at different sensing strategies and how those kind of impact the reconstruction. Yeah, so there are a number of interesting findings in this paper. I think we explored several different fluid flow fields we're trying to reconstruct, and we used several different sensing modalities. So things that, random sensors, lines of sensors, windows of the flow kind of to mimic PIV sensing and things like that. And I think one of the main findings, at least from my perspective, is that across these flows, it is pretty robust to different sensing strategies. You can get a dramatic reduction in the number of measurements you need of that flow. And because there are these dominant patterns in the flow, you can still reconstruct and estimate pretty faithfully with relatively few sensors. And it's not that picky or finicky about where and how those sensors are placed in lots of cases. Some of the surprising results for me personally, and this is just a gap in my knowledge when we wrote this paper. One of the things we did was we scaled from very simple laminar flows like flow past a cylinder to much more complicated flows like the velocity field in the Gulf of Mexico, which is turbulent, multi-scale, pretty messy. And I didn't really understand at the time or know about this notion of decorrelation length, where turbulent structures here would be kind of statistically decorrelated from turbulent structures here, let's say in the Gulf of Mexico. And that has a pretty dramatic implication for sensing that you can't just use sparse sensors in one location. You have to have sparse sensors really kind of distributed throughout because of that turbulence decorrelation length. So for me, that was something I just didn't know about and was very helpful in categorizing sensing strategies for different flows. It really depends on the complexity, how multi-scale it is, how you have to distribute your sensors. That's a great question. And I think this is one of the things I appreciate most about research is, you do a study, you try to like understand something in a really fundamental way, and it opens up so many more open questions and fundamental things you don't know. So I would say on the applied side, based on this work and several follow-up papers from the community, there are questions about how to actually do this on engineering flows. Let's say you have a wing, a Boeing wing, and you're trying to put a few sensors down to estimate flow structures. How do you optimize those locations to maximally inform the flow patterns that you're likely to see in that particular physical regime? And so that involves, writing this down as an optimization problem, maybe adding physics constraints, and that's a very applied problem. Going back to the insect problem, it's also quite interesting to understand the co-evolution of sensing and aerodynamic structures. So on wings, like insect wings, they actually place their sensors on veins. And so those veins give blood to the sensor, but they also rigidify and change the structural properties of the wings. So understanding that coevolution of the sensing and the flow generation itself is a very deep question. I think that'll take, at least a decade to really address in a satisfactory way. And then from a more methodological point of view, we based our entire analysis on linear flow reconstruction, linear patterns, these POD modes. But the community in the last 6, 7 years has moved, aggressively towards neural network autoencoders and nonlinear pattern extraction in these flows. And so taking the same kind of analysis we did and moving that over to the kind of neural network nonlinear representation world, I think will be really interesting and we'll probably get surprising results when we make that step. Yeah, I think that one of the reasons this paper resonated with the community is that we observe flows all the time as humans. We see clouds, we see airplanes, animals, birds, and insects, and we see that even though flows are extraordinarily complex to describe, to simulate, or to measure in an experiment, again, there are these patterns that are useful, they're beautiful, they are recurring, they just show up over and over again. And we've known that for a long time. For 5 decades, we've been extracting these modes and these patterns from flows. But this is kind of a dual perspective. The existence of patterns also means you can do more efficient measurements and more efficient estimation, more efficient control. And I think that's something that the community has deeply believed for a long time. And this is just another technique, to bring sensing and reconstruction into that. So, so I think that's kind of satisfying to go a little deeper into this picture of flows have patterns. Those patterns are useful, and you don't have to measure everything in the flow. Yeah, so this work has definitely had a big influence in my research group. We have had a pretty major focus on sparsity and reconstruction and estimation for a while, but this was the first paper that really applied it to complex flows, exposed the limitations, looked at different sensing modalities, different flow regimes. And so for me, I think that was the first paper where the rubber really hit the road and we started getting into real complexity. And it gave us a lot of confidence that, we could tackle more complex flows than just flow past a cylinder or kind of the toy problems we had been working with. Thinking about where to publish this work, PRF really was kind of an obvious first choice for us for a number of reasons. So it's one of the absolute, top journals in fluids, which is great because we felt like this was a pretty significant result, and our audience was not machine learning people. It was not, necessarily control people primarily. It was primarily geared towards the fluids community. Which PRF is, central in this community, but also, my work for my entire career has been interdisciplinary. It's been at intersections of different fields, and so this is at the intersection of, fluid dynamics and sparse optimization, or let's say machine learning optimization. And the other thing I thought was really nice about PRF is we felt confident that we would get fair reviews and also that this wouldn't be kind of a closed-minded, stodgy, stuffy community where, it's not fluids enough, right? Like having a new interesting result in fluids that was based on a different literature is seen as a good thing often in PRF in my experience. And so for me, that was, really an easy choice. It's, central in fluids. It got our community that we were trying to present this to kind of front and center. And they're very open to innovative new ideas and things that are not just like kind of classic black and white traditional ways of thinking. So yeah, and I think probably PRF is where I've published most of my work in fluids if I look at like the majority papers. I think that consistently, because of its openness to interdisciplinary, I've chosen mostly to publish in PRF. And actually recently joined the editorial board, so that was really nice. Thank you for inviting me and welcoming me onto the team. So I handle mostly machine learning and fluids papers, which again I think is really great that there's a focus in PRF for these kind of intersectional or cross-cutting ideas.
Steve Brunton was discussing the paper Robust Flow Reconstruction from Limited Measurements via Sparse Representation, co-authored with Jared Callahan and Kazuki Maeda. The paper was published in Physical Review Fluids in 2019. Thank you, Steve.
Thank you.